It's really exciting to be here with you today. Thanks for coming to my talk. I know there's lots of other talks that are going on that are also really interesting, so thank you for being here with me. But I do want to talk about timesharing. I got really interested in this topic last year, actually. I did a talk for another conference, which was sort of the early history of concurrency/distributed systems. And in that talk, I went through about 15 years of history in 50 minutes, something like 21 papers. Anyway, a big part of that was like centered around operating systems that dealt with concurrency. And so I really got curious about where did this idea of timesharing come from. I think most of us in this room are a little bit familiar with the origin story of Unix in terms of, it got created in this small research lab, and just sort of grew and grew and grew, and there was sort of a number of very fortuitous circumstances that led to Unix becoming quite popular. One of the big ones being that computers cost significantly less than they did in the 1950s, and the second one was that Unix was a portable, quote unquote. It was able to be moved from system to system to system, and that was something that was actually quite useful and unusual. Certainly the systems we're going to talk about today are very tied to specific hardware implementations, and all of the time-sharing implementations that I will be talking about today are very tied to specific hardware properties that those systems provided to their software developers. So this is the agenda for today. I want to start off talking about Project Whirlwind. Project Whirlwind, as we're gonna get into here, is a really interesting project that was started in 1944. It was started at MIT, and one of the reasons I wanted to talk about it is for two reasons. One is that I think the sort of super early history of early computing is really interesting, and Project Whirlwind is certainly one of the earliest parallel computing platforms. In fact, if you look on Wikipedia, they sort of say that it's the first supercomputer of its day. I don't know if I would be that grandiose about it, but it's a pretty impressive engineering achievement. And also, I think the history of computer memory was really fascinating to me. So I'm going to tell you about it because you're already here. So yeah, you're kind of stuck. So sorry, you're going to learn about computer memory in the 1940s today. Hope that's all right with you. The next, I want to talk about the origins of timesharing. So this is kind of like a quick sketch history of like who came up with the concepts and how did they come to be popularized. And we're going to dig into that quite a bit. Then we're going to see our hero protagonist appear, is a man named Fernando Corbató. We're going to talk about him quite a bit today. He actually ended up working on Project Whirlwind and was at MIT and built this system called CTSS under the supervision of some professors there, and he later became a full professor at MIT. And finally, we're going to talk about Multics, which is sort of the immediate predecessor of Unix. Certainly many of you may be familiar with it from the discussion of how it impacted Unix history, but we're going to talk about Multics a good bit today too. So let's get going. Because I do have way more material than I could possibly talk about in this time slot, so yeah, time is precious. But hopefully I will have enough time for some questions, but anyway, let's get going. So as I mentioned, Whirlwind started in '44. It was a project by the United States Navy. They wanted to build an aircraft simulator. They had a lot of aircraft that were brand new towards the tail end of World War II. It's very expensive to train new pilots, and it's especially expensive to train them in actual aircraft that can crash and kill people. So what they wanted to have was a simulator. This might sound familiar. They wanted to build a simulator that could be controlled by some machine or some apparatus that would simulate flight instructions. So as a pilot would move the control stick around in the simulator, the surrounding sort of artificial environment of the simulator would change with it. And this was led by a man named Jay Forrester, who is actually a fairly famous MIT professor. He started on this project in '44, as I mentioned, and worked on it for a number of years. They started out building an analog computer. They felt like an analog computer would probably be fast enough, and that was actually quite a common decision to make at the time. The number of electronic digital computers in 1944 was very small, and there's really only a handful of them in the whole country and even in the whole world. So they built this analog computer, and it just wasn't fast enough. It couldn't do the computations quick enough to respond in real time to a human moving the joystick. And I think something that's really interesting to me is a parallel that we see with virtual reality developers today. One of the big things that they have to deal with is this latency between the time when your head moves and the perception that you have changes. And they were dealing with the same thing in 1945 when they were building these experimental systems to try to build flight simulators. So they built an analog computer, but it's too slow. It didn't work well enough. And so what they decided to do was build a digital computer. One of their team members went to the University of Pennsylvania, where they had built a machine called ENIAC. That's really a fascinating machine. And if you're interested in that, there's a really great book that you should buy, whose co-author is actually sitting in the audience today. So they saw ENIAC, and they thought that, well, maybe what we should do is build a digital electronic computer. And that's what they set out to do. So the specs of this were that they needed to be able to do tens of thousands of computations per second. And they were able to achieve 20,000 ops per second in 1952. They felt like that was the lower bound of acceptable. The actual specification was to do 50,000 operations per second. And they were able to achieve that later in like 1957. But the biggest issue and the biggest blocker that they had at the time was that the memory system was too slow. I just wanted to show you, this is a photograph of Jay Forrester. He's working on this console back here. And then over here on this side is the actual sort of output module that controlled the simulator. The thing that was really interesting to me is this is a lady. I don't know if you can tell that. But there's been significant achievements and contributions by women in this field, even from the earliest days, working on computing, even in the 1940s. All right. So this is a great quote that I found in a paper that I read about Whirlwind. It was written by Robert Everett. Robert Everett was one of the chief engineers that worked on Whirlwind. He was Jay Forrester's kind of assistant. But I think this is true now, and it was certainly true in 1952. He said, what the computer business needs and has needed and will probably always need is bigger, better, and faster storage. Okay, who disagrees with that? No one? Okay. All right, so let's talk about computer memory, because I told you we were going to. So now it's time. Whirlwind needed 2,000 16-bit words of memory. And in the 40s and early 50s, there were only two types of memory that could provide that much capacity. And I know that sounds like a minuscule amount. That's basically like 4K of what we consider to be memory now, which is, literally you cannot buy chips that small anymore. But in the 40s and 50s, there were only two types of memory that had that capacity. There's one that's called delay line, which was a really interesting system that we're going to talk about next, and then another that is called electrostatic, that uses magical physics that I don't understand. So don't ask me a lot of questions about it, but that's how they did it. So delay line is a really interesting technology that had its roots in radar technology from World War II. It was actually invented to remove static objects from radar displays. So if you send a radar signal out into the world, objects that are not moving will always respond in a constant time. And early radar systems didn't have a way to remove those, and so operators would get confused by really tall buildings or hills or things that were obstructing the radar signal, and they would give erroneous information to pilots that were scrambled to go off and fight sorties. And so what they wanted to have was a way to eliminate them from the display system, and they came up with this technology called delay line. And what delay line does is it basically delays a set of information for a given amount of time. And this was what it was originally used for. So they would send the signal out, it would come back, it would be processed, they'd send it through this delay line signal, and then things that were didn't move in that amount of time basically were removed from the image. They could take the original signal and the one that came through the delay line and merge them together, and they would cancel each other out. Excuse me. So in delay line memory, bits are represented by sound waves. They had a microphone that sat out at one end of the delay line, and it would emit sound signals into a medium. They used mercury for this. There's a lot of reasons why mercury is a less than ideal substance to store information in. One is that it's really heavy, and two is that it's really toxic. And the third reason is that it's really hot. Because sound moves through mediums at different speeds, at different temperatures, The delay line circuits had to be kept at a constant temperature of about 40 degrees Celsius, about 100 degrees Fahrenheit. And the picture that I have over here is this is Maurice Wilkes. He's a really famous computer scientist from Manchester, and he built the EDSAC. And he's actually, it's hard to see in this photo, I'm sorry, but he's actually down here inspecting a coffin. And they had all these delay lines that were like, 18 feet long, tubes of mercury that weighed, about 25 pounds apiece. They had over 500 pounds of mercury in this whole system. And they would be heated up in these coffins that actually laid between the racks of computer equipment. And that's how they stored their memory. One other interesting thing about this that I found out was that one of the primary inventors of delay line memory as a storage technique was a man named Presper Eckert. And you may know Presper Eckert as was one of the entrepreneurs that started UNIVAC and also worked on ENIAC and some other early computing systems. And so he actually worked on radar systems in World War II, and that's how he came to deal with this engineering principle. All right, so let's talk about electrostatic memory now. This is a picture of an electrostatic memory tube. It's about this long. It's probably about that long. And that entire tube stores 1 bit of information. And it also cost $1,000 in 1940. That's $10,000 in today money. And it lasts for about 1 month. So you get 1 month of storage for 1 bit for $10,000. Okay, and remember that you need 4,000 of these. Okay, so yeah, so this is not a cheap thing to do, right? And so Jay Forrester was like, we can't afford to buy 10,000 or 4,000 of these things because we don't have, even the US government was not going to pay $4 million for them to go out and buy all these electrostatic vacuum tubes. And so he was like, there has to be a better way to work on this. And it turns out that there is a better way. There had been some really interesting and groundbreaking physics that was going on at the time. In about 1948, there was a breakthrough in magnetic storage technology. And the breakthrough was that they had finally worked out a system where they could charge a toroidal magnet on a grid. And they could apply a charge to it selectively. And they could use that to replace all of this stuff. And so that's what they invented. This is magnetic core memory. It was patented in 1951. It was invented by Jay Forrester, who we've talked about a few times already. Essentially, the way that it works is you can see that this grids, basically. There's columns and rows, and at each intersection here, there's a little toroid, which is a little iron donut, basically. And they would apply a charge to that, and it would selectively apply an electromagnetic field to it, and it would charge itself, and then they could tell if the presence of electromagnetism or not would indicate if a bit was to be stored there, right? And so it was random access. Something I left out that's really important about delay line memory is that it was sequential, right? And on EDSAC, it took about 400 microseconds to cycle through an entire storage array of memory. So if you needed to store a bit at bit position 10, and you were already at bit position 50, then you would basically have to wait for the entire thing to cycle through again before you could inject the new value into the memory stream. So clearly it was too slow, too expensive, too toxic, too heavy, too hot. So there's a lot of reasons why they wanted to invent stuff like magnetic core memory. All right, so it's reliable, fast, cheap. Like I said, it was invented by Jay Forrester, and they specifically built this core memory. This picture is actually from a part of Whirlwind, and like I said, they finished it in 1951. And in 1952, when Robert Everett wrote that paper I quoted earlier, they were still using electrostatic memory. But within a couple of years, they had replaced all of the electrostatic memory with magnetic core. All right, so let's talk about the origin of timesharing. Again, I think this is a really interesting topic. Excuse me. All right, so everyone probably knows who this is. If you don't, it's John McCarthy. He was a professor at Dartmouth in the early 50s, and he later came to MIT as a doctoral research fellow. So he wasn't even officially on staff. He came to MIT in about 1957. And he did all sorts of interesting things like invent Lisp and garbage collection. He worked on Algol for a number of years. If you're interested in sort of more in the biography and history of John McCarthy, I did a talk a couple years ago at Strange Loop about early programming languages. And if you're interested in that, I highly encourage you to watch it. It's on YouTube. He won a Turing Award in 1971. So he's pretty famous. He wrote this really interesting memo in 1959 where he proposed to the director of the MIT's Computation Center. His name's Professor Philip Morse. Morse was the director of who was in charge of the relationship between MIT and IBM. At the time, IBM and MIT had a really close relationship, and IBM was actually giving MIT millions of dollars worth of computing equipment for free, essentially to train engineers to use IBM equipment later when they graduated and went into industry and stuff like that. So he wrote this reminiscence, and what I really wanted to do here was try to describe what timesharing means. And in the sense that John McCarthy meant it, because there's an earlier paper in 1959 by Christopher Strachey, who is a professor also at Manchester for a long time, and actually talked about yesterday at Rachel Reese's talk about the history of F#. But anyway, Strachey wrote this paper in '59 that talked about using timesharing as a debugging aid. But John McCarthy was thinking about it really as a way to interact with computers in a totally new and different way, where every user could pretend that they completely controlled all of the computing device. So they could use the computer as if no other users were using the computer, even though many other users were actually in reality using it. And so he describes that in this reminiscence. And I think it's important to talk about what the sort of normal mode of operation was in the 50s, and that's this, it's batch mode. So what they would do is they would take a whole bunch of jobs that usually came on punched cards. They would run the punched cards through a secondary computer, and those would get written on a magnetic tape. So the magnetic tape would be the unit of transfer. They'd take the magnetic tape off the secondary computer over to the big main computer. They would run all the jobs from that one magnetic tape through the big computer, and this might take hours, and then it would go onto another magnetic tape that was the output. They would take that magnetic tape off the main computer, go back to the secondary computer, and then they would do line printing. So it would print out all the results from all the jobs that got started during that batch run. So it was like a bus, right? So everyone gets on the bus goes somewhere, everyone gets off the bus, you're done. And this was super frustrating for people, especially programmers who wanted to have more immediate feedback on what their programs were doing. As a single error would basically cause your entire run to abort, it could be hours or even maybe days before you got to run your program again. This is what McCarthy said, and I think it's a really good quote. Computers were developed with this idea that programs would solve general problems, and the time would be spent running these standard programs against new sets of data, but the actual situation is closer to the opposite. And this is this memo that I mentioned earlier that he wrote to Philip Morse. And Philip Morse was supportive of the idea, but as Corbató mentions in an oral history later, that he didn't appreciate timesharing. He didn't really understand that it was something that was revolutionary and new. The thing I love about this quote is that Corbató says that the appreciation of timesharing was proportional to the amount that you personally programmed. Right? The more you program, the more you knew what it meant, the more you understood how valuable it was and how new it was. All right, so I wanted to run through a quick timeline. I felt like the best way to do that is to just build a chart. So in 1957, McCarthy arrives as a research fellow. He proposes right away, at the time they had an IBM 704. A 704 is a super early IBM computer, total 100% vacuum tube technology, very slow, very cumbersome, extremely expensive, but also quite productive. Many people in industry already had one, especially very large companies like engineering heavy firms like Boeing, aircraft companies, car companies, stuff like that. So IBM had already done a real-time, what they called a real-time package that allowed Boeing to input wind tunnel data into their IBM 704. And so IBM had already done the engineering work to do interrupts and things that were necessary for doing, quote, real-time operation, like interactive timesharing. And so he proposed that MIT acquire one of these and modify their computer and move forward with that. So they made this request, but it actually wasn't delivered for 2 more years. So in 1959, IBM delivered a new version of their software, or their hardware, called a 709, which is also all vacuum tube. It had all these real-time modifications that they had asked for, and he demonstrates some interactive Lisp with one of his students. This is a very crude custom system. So they had a professor at MIT named Herbert Teeger, and he was the leader of the time-sharing committee that they'd set up, and he actually modified, built from scratch, 3 flexowriters, which were like these, basically electric typewriters that had computer output, and he modified them to be able to interface with the uplinks for the wind tunnel modifications. But one of the things about Teeger was that a lot of colleagues at MIT felt like his ambitions were vague, and so they didn't support him very well. And then I mentioned about Strachey down here. He published this paper at a very large conference in Paris in 1959. It's called Timesharing in Large Fast Computers, but it mostly deals with this idea of multiprogramming. If you're interested in the history of multiprogramming, I did a talk last year about that, which is also on YouTube, and you can find it. But McCarthy had this idea of a virtual computer that's a little more expansive and encompassing than Strachey's concept. All right, so McCarthy starts consulting with Bolt, Beranek, and Newman in 1960. He happens to run into someone named J.C.R. Licklider. Licklider is also a really interesting guy. He's pretty famous. He's written some interesting papers. At the time in 1960, he had just finished writing a paper called Man-Machine Symbiosis, which is a really fascinating paper, and if you're interested in that, you should read it. But he talks to people at Digital Equipment about time-sharing, and he also talks to a lot of other people, including J.C.R. Licklider, about time-sharing and how useful and revolutionary it is, and they agree with him. And so they start working on their own parallel time-sharing projects in concert with MIT. In fact, Digital Equipment gave MIT a PDP-1 to work on a time-sharing system that's worked on by Jack Dennis, and Jack Dennis and his students have published quite a bit of papers about time-sharing too from this general time that are interesting and worth looking at. All right, so then in 1961, the Computation Center is run by Morse, as I mentioned a few times, and they finished an early version of CTSS that runs on the 709. Now, keep in mind the 709 is all vacuum tube technology. It does not have any magnetic data storage outside of tapes and punch tapes, punch cards and paper tapes, and some of these flexowriters, right? They had these 3 special flexowriters that had been custom built, and it's led by this man named Fernando Corbató, and timeshare is demonstrated by Corbató also. He writes this paper that I cite later on in my talk. And then in 1962, there is the functional prototype. So this is a little bit more cleaned up, and they call it CTSS. He writes this paper, and it enters regular production usage in 1963. One of the things that's very important about 1963 is that IBM finally supplies a transistorized system. So one of the big changes that happened from this timeline from all the way over in 1957 to 1962 is that transistors were invented and become available on commercial scale. So they can start building computers out of them. And transistors, as you might imagine, are about 30 to 40 times faster than vacuum tubes. So it's huge, huge, huge. All right, so this is Fernando Corbató. I've already mentioned him a few times. He actually was an electronics specialist in World War II. When he graduated from high school, he went into the Navy, and this was before he went to college. So he was in the Navy for a long time, and he learned how to do radio technician work and sonar work and a whole bunch of other electronic things that the Navy was putting on ships. After he left the service, he went to Caltech in 1950 and studied physics because he was interested in physics. And then later he went to MIT to get a PhD in 1956. And at this time, he started working on Whirlwind. The reason he wanted to work on Whirlwind was because he needed to do computations for coefficients in his physics works. So generating the coefficients by hand was quite laborious and took a long time, and the computer could spit them out in a matter of hours. So that's how he got involved with programming and understood that real-time interaction was very valuable to him. He was also the deputy director of the Computation Center later, and he led the design on Multics and also programmed most of CTSS. And he won a Turing Award in 1990 for that work. Here's the video that I briefly played earlier. In this video clip, I just wanted you to see this. There's a fantastic video of Corbató demonstrating the entire system for a public television program that was shown in Boston in 1963. Corbató actually had a digital copy of this. It was transferred to videotape and then to CD, and then now it's on YouTube because everything ends up on YouTube. So anyway, this is Corbató kind of explaining how timesharing works to the reporter that he was working with.
What we have is we actually have one master program, which I'll call a supervisor. And this is the program that is going to run everything. And normally this computer, when it's in the time-sharing mode, is operating a program in the supervisor. We also have a program for each of the typewriter users, say U1, U2, U3, U4, and so forth.
They might not be the same size as you've indicated.
No, they're not all the same size. That's quite right. That's what I meant to try and convey. But, now, the consoles have to type in to the computer, and they type into the supervisor and back out. So the messages are handled by the supervisor for each of the programs. Now, the supervisor is going to relay these messages to the particular programs as they are, and keep track of which user's talking to which typewriter, of course, and so forth. And this would be straightforward enough, except that quite often we'll get more programs than we have room for.
Yes.
All right, so that's one of the problems they had, was that they had more user demand than they had resources, right? So they had to share them somehow. And we're going to get into some of that in just a few slides here. I'm going to give McCarthy the last word here. He says, I still don't understand where all the computer time goes in time-sharing installations, and neither does anyone else. So, there you go. All right, so we talked about CTSS. As I mentioned, the prototype ran on the 709. The supervisor ran in the core memory, and all of the other user jobs were in higher memory locations. And the neat thing about CTSS and the reason it was called compatible was because it could continue to be used in batch-style operation even as time-sharing users were connected to the system. So that's how they meant compatible. Most of the people at MIT called it the CTSS, and they never even knew what CTSS stand for. They just knew that it was the system that they used to log into the computer and run their programs. So I wanted to talk just quickly about the effort and the size. Just to give a sense of like how much work was involved in building the system, there was a really interesting paper that was put out in 1966 by Jerry Salter. He actually was a really interesting guy who wrote a bunch of interesting programs that, as I probably tweeted, and if you follow me, maybe you saw that, but one of the things he wrote is a program called Runoff. Runoff is like the earliest version of ROF, which you may be familiar with, and then later, turned into stuff like LaTeX and other typesetting systems. So this was like this was a paper that he wrote. So he described how long it took and how much effort it took. But the contemporary compilers of the day, so things to run Algol, things to run Fortran, those systems weighed in at around 11 to 16,000 words. And a word in this sense means an 18-byte or 18-bit. Sorry, not 18-byte, 18-bit word. So we're talking about, we think about bytes as 8K or 8 bytes, or I'm totally getting confused. We think about bytes as being 8 bits, and in those days they had 18-bit words. So that's, a little bit bigger than 2 bytes. And the CTSS supervisor was 12,000 words, and then they had 6,000 more words to describe commands. So some of the commands that people could use were log on, log off, edit, input, load, start, sort of the standard system, utilities that you might expect to have in a time-sharing system. I think just, for interesting contrast, my slide deck here, including the video and all the pictures, is about 100 megabytes. So it's significantly bigger than the CTSS supervisor. So I also mentioned that Corbató was the lead. Some of the other programmers that worked on the system were a lady named Marjorie Merwin-Daggett and Robert Daly. And they also wrote papers and had published works about CTSS that are interesting, co-authors on one of my citations. So Corbató said that most of the battles that they fought during the development were solving problems that that no one ever had thought about solving before. And some of these things are like memory protection, I/O device, how to decide who gets to see what messages, saving and restoring user state right between time slices. When it's time for your slice to go off the CPU, how do you store it? How do you get it back into memory? Also, how much time does a user get? Like, what's the right time slice to give a user for their computations? How much do they deserve? How much do they get? And then, is there satisfactory responsiveness, right? So, if you press a key on the typewriter, how long is it before you see a response from the computer? That's actually something that was interesting. This next slide is a great picture. We've all seen pictures like this, right, in our graphs and metrics systems. So this is from a paper that was published in 1962, and what it describes is the service level versus the number of users. We're all familiar with this curve, right? We hit that point N, and then basically it goes to 0. Corbató saw that a long time ago and wrote about it in his paper. So Corbató described this as a breakthrough success. In later writings and in oral histories, users were very satisfied with CTSS. They were very happy with the online storage of programs and data. They could do remote operations. Remember, prior to this, you had to drop off your card deck somewhere, and then later you would magically get a printout of your results. Now you could go to a computer terminal that was not necessarily right next to the machine, but could be in your office, or it could be in your professor's office, or it could be in your laboratory, and you could interact with the computer, run your data sets, run your programs, and get results right away. And it also made it really convenient for users to share information between one another. So, if a professor was working on a program and his colleague wanted to look at it or be able to access it, it would be possible for him to do so. In the past, it would be very difficult to share that kind of information with someone else. All right. Also, transistors and random access disk files are really important. So one of the things that I cut the video off, but Corbató goes on to explain how the disk devices that they had made it possible for them to store very large quantities of data. And by very large, I mean for the day, right? Like in absolute context, my phone has way more storage than all the computers at MIT for the entire 60s. But certainly for the time, it was very, very important to them. But users, once they got used to CTSS, started to demand some improvements. They were satisfied with it, but it could always be a little better, right? We've also heard this from everyone. So users who endured hours of waiting for batch processes would be annoyed by the fact that it would take a second, for a response to come back from a computer. We've all been there, right? A one-level file system, right? CTSS had a very simple one-level file system. You can imagine that over time, that gets really cluttered. And it's hard to figure out what's yours and what's new, what's dead, what needs to get rid of. And then finally, he felt like the more we provided them, the more they wanted, which I think all of us can sympathize with that too. One really interesting thing that happened during CTSS one day was, as the system grew in importance and also in complexity, they had about a dozen system programmers. The system programmers were responsible for maintaining and extending the system software, and they had an editor system. And the editor system had an assumption that was only one person could be logged into a directory at one time. And so the editor wrote a temporary file with a static name. It used the same name for every file. Well, one day, a system programmer at one terminal logged in and started to edit the message of the day. And in another terminal, another system programmer logged in and started to edit the password file. And so what happened is that the password file got put in as the message of the day, and the message of the day got put in as the password file. And so what happened when you logged into the system was that you saw everyone's password in clear text. And this is before they ever had like one-way hashing functions, and certainly computer security was not even an afterthought at all. So that was a big problem. Fortunately, what they had was that any user could actually crash the system. What they would do is go into a debugger mode, and then they could type in a direct assembler. They could type in assembly directly to the computer CPU. And one of the instructions that you could do was called XEC. And XEC would put the computer into an infinite loop, and it had to be hard reset, right, completely shut down and restarted. And so what happened after this is one of the system programmers saw that, dropped into the debugger, typed in XEC star, hit enter, and then the computer crashed. And so no one could log into it. So that's what happened. He recounts that in one of the papers. Also, if you're interested in that story and the full context, I have a citation for reminiscence from one of the system programmers who talks about that event too. So let's talk about Multics in the last little bit that I have left to talk today. So first of all, I want to talk about some myths. And a lot of people think that Multics was a failed system, that it was never completed, it was never released to production, it never ran anywhere. But that's not true. And we're going to talk about why that's not true. One of the questions that I've asked is why? Why do we want to develop Multics, right? CTSS is really popular. Everyone's pretty happy with it. I mean, there were user complaints, right? But there's always user complaints. You could have the most perfect system in the world, and someone would want it to be different somehow. But basically, the development team felt like they could start over. So they learned from CTSS. They really felt like it was a prototype. It was a mature prototype. It was successful. People were happy with it. But they felt like they could do more. They could really, if they just threw away everything and started over from scratch, famous last words, then it could be a lot better, right? We've all thought this, right? Has anyone here not thought that? I mean, all software developers I know always think, well, if we just get rid of the old system and I could just write a completely new system, it'd be a lot better. Well, they had the same thoughts about, let's build a new time-sharing system that's really going to be great. So one interesting thing about Multics that was unusual at the time was that they spent a lot of time trying to find industry partners. So this was not just an MIT-led project. They wanted to find people in industry to work with them. And one of the reasons they wanted that was because they had some ideas about how they wanted to handle memory protection and other things that require hardware support. And at the time, IBM was really not interested in pursuing this. They felt like batch operation was, great for everyone, and they sold lots of computers doing batch-style operation, and there was no reason that you'd ever want to do time sharing. And the systems that they were working on, the platforms they were building at the time, didn't lend themselves in a hardware level to doing time-sharing systems. So they went out and they found a partner at GE that had a new computer division. They just started because in the 60s, every company that was large enough built computers, like literally every company you can think of. There's like 7 of them, I think. Philco, RCA, General Electric, Honeywell, Burroughs, Sperry Rand. At the time, they were called Remington Rand. And remember, Remington Rand is a company that builds typewriters and also ammunition cartridges and other things. But anyway, everyone built computers in the 60s, and so they found partners at GE and Bell Telephone Labs, and maybe that's where you've heard about Multics in the past. Here's some firsts that Multics did in the system. It was the first one to use memory segments and pages, so maybe you're familiar with the idea of pages. They had privilege rings around the kernel, so there were different privilege levels, and as you moved up in privilege levels, you got more memory access. This was a means to protect programs from malicious users and also from errors in the kernel code. The virtual memory system, including this idea of swap, and mapping files to virtual memory is something that Multics accomplished. And the hardware system could be composed of multiple CPUs, RAM banks, storage devices, and they could be reconfigured online. So you could modify the system online without having to take it down. And one of the other firsts that's really unique for Multics was that it was written not in assembly language. So if you follow the history of computing programs, you'll see that writing things in not assembly was very uncommon, especially for operating systems. So they decided to use this language called PL1 that was the new hotness. I might call it the JavaScript of 1965. It had good points and bad points, let us say. Why did it take so long? So Multics started in 1965, 1964, and it really wasn't delivered as a product until 1972. And that's an extraordinarily long time. And famously, Bell Telephone Labs dropped out of participating in this project because they felt like it wasn't moving fast enough for them. And that's kind of the genesis of where the Unix creation story starts, is at that point in '69. Anyway, it took so long for a number of reasons. Some of them was that there was no benevolent dictator for life. There was no arbiter of taste. It was all these companies trying to work together. There was no decision maker that could say, yeah, that's a good idea. That's not such a good idea. They would have to basically build up prototypes and make sure that they were strong or weak. Something else that was a big problem was that there was no functional PL1 compiler until about 1967. So they were already 2 years into their project before they actually had functional compilers. Before that, they were using sort of compilers that were built ad hoc, were partially complete. that used languages like BCPL and stuff like that. Interestingly, Rachel Reese talked about BCPL yesterday in her talk, so if you missed that, you should watch it later on YouTube. This is a great quote from Corbató. He says, "There was a brutal period when we discovered we built a monster. There were a lot of instances of that inside Multics. One of the problems was that we were all young and naive. We couldn't see we had built something that was complicated. Only under the duress of realizing it was awful did we dig in and realize it didn't have to be that way." I think we've all been there at one point in our careers. And then something else he said that I really liked was, "It's trial and error aspect of system synthesis, which I think is a major factor that people underestimate, and a huge amount of the difference between engineering projects, to me, is the degree that the participants have done it before. If they've done it before, it's a piece of cake sometimes. If they have never done it before, it can be a hellish adventure." All right, well, I think we've all been there too. And then finally, there's this one which I thought was really interesting, which something that I had immediate question was, in 1965, choosing PL1 was a pretty bold, risky thing to do. And so he provides some rationale why they did that. He says, in retrospect, it was a monstrosity to use this. But our conviction was that we had to have a compiled language, and I think it was dead right. The next problem was that we wanted one that was relatively advanced and flexible, and there weren't many choices, and that is true. The third key ingredient was that Doug McElroy and Bob Morris at Bell Labs, who had considerable expertise and wanted to take responsibility for languages, was quite persuaded that PL1 was a good choice. So their partners had told them and sort of cajoled them into being able to use PL1 as their primary development language, but it turns out that maybe that wasn't such a good choice, and Corbató, in retrospect, agrees with that assessment. So anyway, Multics was a successful product. In 1970, Honeywell, the people that make thermostats, they acquired GE's computer business from them, lock, stock, and barrel. They also acquired all of the Multics IP that General Electric had been working on. And the team at MIT and Honeywell worked together to complete the system in 1972. It was commercially available for a number of years. It was mostly bought by government military installations and installation sites, and actually started to run some of the radar systems and defense systems that would track missiles and other flying objects, not UFOs, but aircraft and stuff like that, aircraft control systems for military installations mostly. So that's what Multics was mostly used for in production, and it was actually available commercially for a number of years, all the way up until about 1987. I think is when it stopped being sold as a commercial product, and then it actually lived on until about 2000. There was a site in Canada that was used for air defense that was turned off in October 2000, and that was the last Multics installation. These days, if you're interested in playing with Multics, there are emulators for all the hardware that you can actually download and run. And there's Multics is available open source now. Bull has the company that owns the intellectual property has donated all of it. It's downloadable from MIT, so all the source code is available. I just want to talk quickly about what is the legacy of Multics. And Corbató said in his 1990 Turing Award speech this. The Unix system was a reaction to Multics, and even the name was a joke. Thomson's strategy was clear: to start small and build up the ideas one by one, as he saw how to implement them well. And as we all know, Unix has evolved and become immensely successful. All right, so that's all about Multics. I wanted to talk about a bunch of other systems because some of these had direct impacts on how Unix behaves too, but I really didn't have time to do that. So I'm just going to mention them in passing and then cite the papers where they're described fully if you're interested in them. Jules Swartz was also a software developer, professor of computer science, who worked at a company called the Software Development Company, which was on the West Coast. And in 1963, they had some excess machines that had been built for the SAGE program. And SAGE was this Air Force, U.S. Navy program to build air traffic control systems for the military. Maybe that sounds familiar. And then the Dartmouth timesharing system, which sort of begat BASIC and has a very interesting, rich history of its own, is an independent timesharing system that was developed at Dartmouth. In 1964. In 1967, at Berkeley, there was this Project Genie, which is a system that Butler Lamson worked on, and it's really interesting. And then finally, at the bottom, there's this paper by BBN called 10X, and then Digital had another sort of sister operating system called TOPS 20. that was, and a paper about that was published in 1972, which is also pretty cool. Anyway, that's what I have, and thank you for your time. And I'd love to take any questions if there are any. So thanks.
Questions?
In the development of the early time-sharing systems, how much did the hardware influence the time-sharing system, and then how much did time-sharing systems eventually influence hardware? Like, what was the interplay there?
Yeah, that's a great question. The question was, how much did hardware influence the software and vice versa? For the most part, in the early days, they had to custom-build hardware to do interrupts, to do things to signal to the computer that it should pay attention to the user input. And so in the early days, it was really hardware-driven, and the software was sort of a side effect of that. In later days, as time-sharing became more prevalent and more desirable as a feature, those features, those hardware interrupts and things they just came out of the box, right? They weren't custom engineering things anymore. You just got them, and it was easier for people to implement systems like Unix that could just piggyback on top of the sort of interrupt systems that already came by the hardware manufacturers. So that's a good question. So in the early days, very hardware driven. In the later days, not really driven by hardware at all.
Hi. Two questions.
Yeah.
First, how big was the magnetic core memory?
How much could it store?
No, how big? You mean the tube was roughly this size?
Oh, you mean like the delay tube was basically the length of the stage, and magnetic core was, how big was it? Mm-hmm. Yeah, it's probably about the size of like a poster.
I see.
Probably like about this big, something like that.
I see. Thank you. And second question: what was happening abroad, outside the United States and England, for all that period? Did you study anything? Did you see anything?
Yeah, so there is a rich history of computing in England that I didn't really touch on very well, and that's mostly because the history of time sharing mostly was focused around what was going on in the United States, and then what was happening outside of that was a reaction to what was going on. So in the UK specifically, there were a lot of systems that were being built by a lot of companies, and also research projects, a lot of which were built at Manchester, and others that were built at Cambridge. And developed by people like Alan Turing and other early computer pioneers. For the most part, time-sharing systems didn't come to the UK until later, like in the middle of the 60s and stuff like that. And by that time, CTSS had already been developed. So that's why I didn't really talk about that. Are there any other questions?
So this will have to be the last question, I think.
Yeah, I think I'm just about out of time.
Thank you very much. I was just quite intrigued when you mentioned the development of interrupts as something specifically driven by user input-output. Does that mean interrupts to drive I/O like we understand it nowadays? Basically, all I/O was polling-based.
So yeah, it was. So interrupts were a thing that in McCarthy's memo he talks about he can't remember who invented interrupts or even where they came from. But the idea that they should be that they should be signalable from a user, from a human, that was a new idea. That was a new concept. Before that, it was all driven by hardware devices. So the magnetic tape system would signal, hey, I have some new input for you, or it would say, I need to write some new output to you. And that's really the way that interrupts worked. It was completely driven, from device to device. And so having it come from a human via a device, that was a new idea. So thank you.
Okay, thank you so much, Mark.
All right.